All right, hi everyone. Let's get going. So where do we stand? This interesting times are continuing. 2 days ago, Intel has acquired Tower Semiconductor, Israeli foundry that is on a bit on trailing nodes. We'll find out what are they trying to do with that, but they're clearly interested in this, in this foundry business, since this is one of the few independent ones that are left over. So let's see how is this whole thing going to play out. You will have some fun figuring this out over the next couple of years or decades. We'll see how long it goes on for. Where do we stand in the class? We have been talking about the current processes and how do they impact the design. We have been we looked at the planar processes that dominate at the moment the volume of things that are being built, and FinFET devices, and we have looked into how do they affect the design choices. We'll be talking more throughout the class this interesting process of selecting processes for a product, and you will find out often this is done by using spreadsheets where you find a blend of performance, power, and cost that impacts the choice for a particular product. There are certain things like models that go into that, and we're going to start dabbling into that today. We have seen these restricted design rules that come with modern lithographies, and we have seen where they come from. There is no way to memorize them all, but when you encounter a design rule error, you at least know the source of where it might have, might have originated. UV at very lower layers, at very low layers in the manufacturing stack helps, but it is not going to be all over in all the layers because UV is more expensive, at least at the moment. And then we have talked about a whole bunch of things that are happening in the chiplet space, but that will also need to play out in the market space, and we'll see how many of the markets does that affect. We have seen that according to a Samsung plot, it is clear for high value products and like hyperscales and so on, and things will there is room for innovation in mid-value products. Now on the low end, things that cost $10 or a few tens of dollars, unlikely that you're going to see big chiplet solutions unless things get really expensive. So the mission of today's lecture is to go over MOS transistors and then start getting a sense of gate delay models. So why do we model technologies? Well, because we don't want to simulate everything at every level of detail. So we would like to have models that traverse the design hierarchy. Eventually, you'll find them in those spreadsheets, technologist selection spreadsheets that companies use, or gurus in companies use at a particular level. But you will find that in the ways in lower levels of hierarchy, trying to model the performance and power of a design before its detailed design is implemented, or modeling the delays of standard cells. We'll follow approach that we have seen in 251A, where we start very simple and then add complexity just when needed. Now, one of the things that you may find it tricky to realize, when do I actually have to add complexity? So, the only way how you can get that is by practicing and understanding what is good for what. When we talk about device models, we'll spend this lecture on IV characteristics for on transistors. Next lecture, we're going to talk about off IV characteristics, leakage IV characteristics, and a little bit about CD characteristics. And then RLC models, we'll mention RNC here, L you will find elsewhere in like 240. So much less time. Well, modeling of RC or interconnect parasitics is much less detailed here. When we talk about transistor modeling, you'll understand different levels, different needs, depending on what we are trying to accomplish. There is some amount that is used for hand analysis, and that is something that a digital designer will do very rarely. We're going to do some of that in this lecture, just to develop the understanding of how do we build standard cells. Then you will find out a similar model is often similar level of models that are slightly more complex hand level analysis models are used for this technology selection, because there are trade-offs in picking things, and by having, before starting to design a product, you have to tell your design team which technology are we going to design this product in, so they don't start designing product in all possible technologies to find out which one is going to be better. You need to have some sense of doing that. What is a typical tool that companies do for that, or these gurus, technology selection gurus in companies use? It's Excel. It's the magical Excel thing where you put your IV models and dependencies of that and build up the whole thing, the model of a whole system in Excel. People have done this in MATLAB and Python and so on, but Excel basically, your favorite spreadsheet does something like that. So we'll also be dealing with some Excel type of models in this class, good for Excel type of analysis. And then there are more things that are more complex, like switch level models that you will find out. These are different kinds of fast spice. We don't use those for hand, but that's when you have a design and you don't really want to wait forever for it to complete the transistor level simulation. Things like NanoSim we might hear, or and so on. And there are some open ones that are out there. And then there are very detailed models that people use for spice simulation, but those things you can't do by hand because you'll encounter hundreds of parameters there. So we are primarily interested in this spreadsheet level modeling or Python modeling. We will practice some of that in homeworks. And what we care about is the performance and delay model. Performance meaning delay models and energy models, and that's our goal. When we talk about transistor modeling, you will find out that there was a lot of stuff done. And this department, this university is really well known for that. This is a group, BSIM, that is done over the past 30-something years. Professor Chenning's group that has been doing many of the spice models. When I was a junior engineer, it looked like all these spice models. I mean, you pick up a spice model from Moses or somewhere else, it's all BSIM group, UC Berkeley. I thought there was like 300 people over here. There was like 5 grad students that were doing all of that. They were really good at fitting those models, and they essentially became, for a long time, an industry standard. Now this is done much more differently and much more widespread, and we don't have really much of a ton of a BSIM group here. When we are doing DC modeling, we really care about accurate IVs, and what we care about also to try to find these. When again, if you're looking at some less mature models and some things that are from non-mainstream foundries, you will find these convergence issues. That means that non-Berkeley quality people have done this smoothing of the curves, and they don't have well-behaved derivatives of the models. in general, we're spoiled now. When I was a student, I mean, these convergence issues were all over the place. Can't find the DC point, sorry. I cannot find the operating point, sorry, try again. And then, there are all these, fudgings that you do to the network, to your SPICE netlist to help it find the operating point. But these models have been built to do that. And then, for transit, you needed accurate IV and QV equations or CV equations. And again, you needed accurate first derivatives for convergence. In general, when you look at these detailed models, you will find a range of physical models, early SPICE models were entirely physics-based. They became much more empirical over time. So there are mix between empirical and physical. They started with a small number of parameters. The number of parameters has gone dramatically up. And there is always this quest to use something that is going to last for generations, and many technologies are going to be able to fit on it. And we have seen changes in there. So the goal for today is to model ion and apply it to sizing and delay calculation. Sizing today, delay next time. So the same thing, next lecture, we are going to do the same thing as we've done in 251A, except that in 251A, I refrained from using any equations. I do not want to scare everybody with equations. We're going to see equations this time. There are two types of models that are out there, or a majority now is EKV or PSP, that is from EPFL, the one on the bottom. The top one is the BSIM, is the Berkeley model. I will be covering BSIM model because it is more intuitive for digital designers. However, SPICE models are not really BSIM anymore. They are EKV. Does anybody know the difference between BSIM and EKV? Ali does spend time on those, to take classes with Ali. So what's the difference between BSIM and EKV? The BSIM, both of them are velocity saturated models. Has anybody heard about BSIM before? No. EKV, PSP. That's okay. All right, and then let's give you we are going to take a look at so if I plot log ID versus BGS, remember how does that look like? It looks something like this. BSIM has two separate equations. One that corresponds to super threshold, and the other one that corresponds to subthreshold. EKV is a model that is able to model that as one equation, as one continuous equation. What's the problem? And that was the reason, motivation for EKV replacing BSIM some 15 years ago. What's the problem of having two equations for subthreshold and superthreshold? As illustrated over here, they don't necessarily match, and at some point you have to switch from one to another. What happens when you switch from one equation to another? Discontinuities are terrible for SPICE. SPICE, it starts going this way and it needs to jump over there. It doesn't know how to do that. So what do we do? What do the device modelers do? They smoothen it out. They go and blend it out over here to make things match. And they were really good at that, but not everybody was good at that, and that caused, if you're not really good at that, then there is a convergence issue. EKV models are not perfect. They're also binned. It's not, even though it's one continuous curve, they have issues with binning per width. So when you're switching from one width to another, you get a different curve, and that can be a bit of a problem. Some people have figured out how to teach analog courses with the EKV models. I have not figured out how to do digital modeling with EKV models. I mean, there is I think Stanford now teaches. By the way, which model presently does 240 use for the last situation? Predictive technology, but what is the model that is underneath? BSIM. So yeah, for me, BSIM is much more intuitive. EKV is this double log, and I don't know how, or double exponential. I can't comprehend double exponentials or double logs, whichever you want to do it. But people have figured out, and there are books written about that. Okay, a few announcements. We have assignment 1 that is very short, will be posted this week. There is no new lab this week, but we do have project proposals that are due next Thursday, and there is no class on Tuesday. Speaking of project proposals, they should be very crisp and easy to understand with a clear mission. They should consist of a title that is meaningful. What is a meaningful title? Like 1 line to 1.5 lines, shouldn't be an accelerator. It should not be an accelerator, an accelerator that does machine learning by using this and that, and applicable to sparse and dense linear algebra. Compact, something in between there. Sparse linear algebra accelerator for medical applications or something like that. Totally fine. Elliptic curve cryptography accelerator. A digital PLL based on this. All right. What else do you need to do to have there? You need to put your names and emails underneath it. It sounds strange, but so many students don't do that. So I don't know how to contact you. Once when I would like to contact you, I need to go look up what your email might be. And that abstract should be no more than half a page. Less than a half a page would be appreciated, but it should have sufficient content in there. And should have 5 references indicating that you understand what is the state of the art. These 5 references should indicate what you think is the state of the art, and your instructors are going to give you feedback whether they agree with you that that is the state of the art or something else may be state of the art. So what would be good projects? I've mentioned crypto accelerators or security things. So we have had a good set of projects that were these puffs, physically unclonable functions. It would be good to move those into perhaps making some kind of EES or very popular nowadays homomorphic or elliptic curve cryptography accelerators. Those things can be well explored and built as an accelerator based on our labs. And there are certain, there are current references, and if you look at ISSCC next week, there are references on that. There are small machine learning accelerators that have been popular, but watch out. I mean, don't build some, people try to build something really, really big. Don't do that. This should be some not really a deep learning accelerator, something smaller, good for an implantable system or something like that, a classifier. More, some people, every semester somebody asks, oh, can I do an analog project here? I really need it for my research project. No, analog is out of scope. You have 240B to do that. But you can do digital PLLs, and we have had some fantastic digital PLLs done in this class. We have done some interest. We have seen digital voltage regulators or digitally controlled voltage regulators, strobe detectors, and stuff like that. Very much appreciated and by analog designers, and let analog designers shine and broaden their scope. Anything else? Run it by us. Any questions? Man, you guys asked like 0 questions.
When is this expected to be given?
Next Thursday. It's not a lot. I mean, this much. This much text. This is a page. This much text and 5 references. But the proposal has to be clear, right? This is the state of the art. This is how digital PLLs are being done now. Here are the metrics that they're being evaluated against. Here is what the best ones have accomplished. We are going to evaluate them, and based on our evaluation, we will make either a better one, move the state of the art, or we'll just make a fair evaluation against this kind of a figure of merit.
Professor, I had a question.
Yes, online question.
Yeah, so I was asking that regarding the number of group members, and if we have like less members, is it okay to like reduce the scope? And if we have more members, is it okay to expand the scope, or is that something which is rigid?
Yeah, so the idea here is that this is perfect for pairs. I really don't want, we discourage solo projects because those are hard to judge, hard to execute. 3-person projects, if you cannot find a group of 2, do it as 3. The expectation here is that you're going to be putting some number of hours, maybe 8 to 10 hours per week over the next 9 weeks or 10 weeks, and that's that's what it is. So that's the size of a project. So 3 people times 8 hours versus 2 people times 8 hours per week is what is the expectation. Make sense?
Yes.
Another question here live.
So can you change the scope of the project, like later halfway through the project, like after you find that it's not feasible?
Yeah, you don't want to completely change. The question is here: can you change the scope of the project? Yes, you can. You can change the focus of the project. You probably don't want to have a complete change of a project. The first phase is evaluation. You will have 4 weeks essentially to read those papers and form your opinion on where the things are. Then you're going to have another 5 weeks after that to build something, either a replica of what people have done. You'll do some paper analysis and say, okay, this is the best way. I mean, there is no way to beat what these guys have done. For this particular application, you're going to build a replica of that, and you're going to demonstrate it. That's good. Or you'll say, hey, I figured out that I can do better. I would like to try to do that. And it's okay if it is related to your research project, if you're a PhD student. I just don't want your research project to be submitted as your proposal. Something overlapping, totally fine, but well defined. It can be done in the next 10 weeks. Any other questions? And this year we're giving freedom. Next year, when we do this again, we might give more of a structured project. Okay, let's dive into our long channel MOS on current model that everybody has seen, perhaps in lower division classes. So the way how this works is like this. We generally say that there is something that is the current density that is labeled as JDS. And by multiplying that JDS by the width of the device, we get the current. In order to get the current density, we find out what is the amount of charge that is inside the channel and multiply it by the velocity. This thing is this is the velocity, lowercase v, and velocity times the charge gives you the current density multiplied by the width of the conductor. In this case, the channel is the current. So the amount of charge that we have inside the channel of a device, if we try to plot that over here, varies with the position in the channel, with the voltage, and looks in general like this. So if this is if these are my drain and source regions, this is my, gosh, okay, I need to change the ink color. Here is my channel, this is my gate, this is my source, and this is my drain. So there is some voltage VGS over here, and there is some voltage VGD. The channel, we can model it in different ways. Usually this is associated with say x-axis. Sometimes they'll call it a y-axis. And if you took a device physics class, this point corresponds to distance 0 from the source. This is the point that corresponds to the distance L from the source. So channel has a length of L. And the amount of charge that we have across the channel varies with the voltage and the position in there. The way, yeah. What is VC? Voltage along this channel. So there is another thing that you will find here. There is another axis that is VC. There is a different voltage along the channel, and we can associate this as some kind of VBS voltage is equal to 0 here, and it's equal to VBS there. So the way how you might have seen this being solved, and I'll try to do it in the next 2 minutes or so, is we'll say that IDS is equal to WCOX times this VGS minus VTH minus VC of X times the mobility, and you pick electrons or holes. An electric field is essentially the VC divided by dx. I take this dx, move it to the left-hand side, and I get IDS times dx equals to WCOX times all of this times dVC. I'll integrate both, and according to what I have on the right-hand side, this will be integrated from 0 to L, and this would go from 0 to VDS. And I'll come up with an equation that everybody has seen before. IDS is equal to W over L times, I remove this, mu COX times VGS minus VTH minus VBS over 2 times VBS. Okay, everybody has seen this equation. This is the equation that governs the operation of a MOS transistor in a linear region before it pinches off. When does it pinch off? When my gate to drain voltage equals VTH, the channel pinches off and the current stays constant. If you would like to plot this, if this is your IDS versus VDS, these things, as plotted over here, look like parabolas that become flat with a value that is equal to IDS being equal to W over 2L times VGS minus VTH squared. So this is linear and this is saturation. I'm hoping everybody has seen this. I've just done the derivation because I'll redo it again after I tell you that this is wrong, and we all know that this is wrong. So if you go and plot this for many of these 28 nanometer models with channel lengths that are pretty long, longer than a micron, it's going to look perfect. And here it's totally 38 nanometer models. It's totally legit to have a 1 micron channel length. So that's all going to work. And what you're going to see here is the spacing between linearly spaced VGS curves. It's going to be quadratic. You're going to have a perfect parabola here, and the separation between the linear and saturation is also going to be a perfect parabola. And the GS minus VTH. Okay, but if we go and plot this for a real minimum channel length transistor, you get something that is much different. Few things that are wrong. Spacing is not quadratic. It's like closer to linear. It is quadratic down on the bottom. Here it's closer to quadratic on the bottom. It is closer to linear to the top. The output conductance or output resistance of these devices when they're saturated is not flat. It is much more fine, so we have much lower output resistance. And the shape of the curves, I mean, there is no clear, there is no nice parabola here. This is something that definitely not a parabola that separates. It's kind of hard to see where is the separation between linear and saturation, but they are there. There is linear region and there is a saturation, but it's not a parabola. What's the reason for this? Is velocity saturation, as we all know. There is no way to fudge this quadratic model to fit the velocity saturation model. You just can't do any kind of fudging, model fitting, to make something that is quadratic look like it's linear. All right. So we need to develop a different model for velocity saturation. People have done that a long time ago, and here is how it goes. The reason for these curves looking very different in short channel devices is the velocity saturation. It simply means that my velocity is proportional velocity of electrons that we have assumed in this derivation that we have done previously, that E is, or velocity, that velocity is equal to mu times E, holds only in a limited region. Somewhere around 1 point something volts per micron of electric fields, the devices become saturated. What does that mean? Well, any device that is of about 1 micron channel length at 1 volt is velocity saturated. So anything below that is essentially operating in a velocity saturated region. So what do we need to do is, well, find where is that number EC, and model fit to that. If you look at different kinds of device physics books, you will find that they have chosen a fit like this, and there are physical explanations why it would be fit by the equation that is equal, that says that the velocity is equal to some mu effective, which is mu that we have been used to seeing for electrons and holes, times the electric field divided by 1 plus E divided by some critical field EC to the power of n, and then everything n through off. They found in the past that you will find a relatively good fit for PMOS devices with n equals to 1. For n MOS devices, a fit of n equals to 2 is more appropriate. Turns out in FinFET devices, both of them look kind of closer to n equals to 1 nowadays. I was told, I have not tried doing this myself. So things can be relatively simply modeled. Again, what you will find out in practical models, like EC models, it's an empirical fit to something that is derived from that. For hand analysis, we have seen a few different ways of handling this. I can come up with 3 ways, all 3 resulting in a legitimate model, each one of them coming with some set of limitations. There is one that is n equals to 1, or n equals to 2 exists as well. Those are the models that were actually put into DC back in the 90s. So physically, literally, the equation fit to n equals to 1 or n equals to 2. We can totally handle n equals to 1 ourselves. Trying to do this as n equals to 2, handling those kind of equations, I mean, you're going to soon, after 3 pages of trying to do those integrals, you're going to run out of space and patience. But n equals to 1, we can totally do in the next few minutes, so you can do it yourself. I'll just give you a hint. More commonly, what you're going to do is we can take a look at n equals to infinity model, which is linear piecewise or curved piecewise. So we'll take a look at those. People have noticed this, by the way, this is not new. This people have figured this out back in the heyday of modeling crowd. So this originates from the 80s in Berkeley. So approximation for n equals to infinity goes like this. The velocity is equal to mu effective times E below anything that is this critical field EC, or is equal to V sine for anything that is above EC. And depending, sometimes, for good fits, they pick this to be EC over 2. Totally your choice. I mean, you can just imagine if you just don't want to go to the point of EC, in order to get a good fit, go pick EC over 2, and the fit it or 2 times EC and get the total fit. So you essentially end up with 2 equations. One of them is the equation that corresponds to a standard device that we have seen before. And the other one is velocity saturated device. How do you divide between the 2? When do you use one? When do you use the other one? It's kind of hard to figure out where it does. When do you switch between those 2? And kind of on the bottom of the curve, you're going to be quadratic, and then you're going to go to more this, constant level up for higher VGSs. And this delineation between VDSAT between the 2 is not that deep. If you have read the old the book that provides Hassan and I wrote or in the early 2000s, we picked some value of VDSAT constant and ran with that. But that causes certain problems if you're going to to address now. So if you look at what is in that book, we picked a model that was essentially a three-domain model. This was IDS, this is VDS. And we said we will follow the separation between the linear and saturation for a while, up to some point, and then we'll say that after we exceed certain value of VDS that corresponds to VDSAT, we will switch to a velocity saturated model. So this would be essentially a three-domain model: linear, saturation, velocity saturation. So this worked okay, but it has a few problems. First, it's kind of cumbersome to handle three different models. You know, having undergrads memorize three different models has been a problem. However, the three models fall into one equation if you nicely budget. And I think Dan came up with that idea, that you can put this thing VGP, or VGP or Vmin is minimum of VGP, VDS, VDSAT, VGP is VGS minus VPH, and this holds. Problem with this model is that it does not handle transistor stacks correctly. We're going to dive into that in a second. But it's something that can be reasonably understood and memorized. So it's, you know, we gave a lot of problems, and you'll find them sprinkled around the internet as well. A lot of people have used this book, and you know there is a lot of there. That this is a model that is suitable for hand analysis, and you can do interesting analysis of digital transistor level circuits, inside standard cells, flip-flops, and so on by using this model. But VDS is not constant, and that leads to some fake conclusions, incorrect conclusions, as we'll see in a second. So a better model is to go and stick with what I've shown and try to model it piecewise, where first velocity will be approximated with mu effective times c divided by 1 plus e divided by EC, up to some point over there that is related to EC, some fraction of EC, and then we'll switch to VSAT when after we exceed that point. How does this work then? We can repeat the exact same calculation that I've, integration that I've done before, but I'm not going to do it because it takes a few extra minutes. So we'll say that our current density is still equal to C ox times VGS minus VPH minus VC times the V. We'll get the current by multiplying the current density by the width. And we can go ahead and integrate that whole thing. Except that instead of V, we're going to put a piecewise model. That piecewise model is going to be what we have had in the previous equation. Oops. Is either mu effective times E divided by 1 plus E over EC or V SAT. And by integrating that, I will end up with a slightly more complicated equation that may scare you early on, but you'll see that it's not too scary whatsoever in about one slide. We're going to end up with an equation that has a part that is familiar. mu x times W over L times VGS minus VT times VDS minus VDS squared over 2. That's exactly the same as what we had before. Totally the same. The difference here is this is the same. This is new. 1 plus VDS over ECL. It kind of scales down the current, doesn't let it go jump up quadratically. It kind of moderates it, pushes it to be more like linear. Remember, this is for the linear region. In saturation, we're going to end up with the same equation, except that we're going to have this parameter VD that is showing up in there, and we don't know how to find the VD sat. Well, we match these two and try to evaluate them at the boundary between the two. We can evaluate what VD sat is. By solving for VD sat, we end up with this equation. VD sat is VGS minus VPH times CCL divided by VGS minus VPH plus CCL. And our saturation current falls out straight from that. What does that mean? If you plot IDS versus VDS, and if I can take my old curve quadratic, parabola that separates the GS minus VTH. Where does this curve sit with respect to the old non-velocity section? To the left or to the right? Well, if the device is not velocity saturated, I would say that it has a very long length, so ECL is much greater than VGS minus VPH. So that will dominate here, it will cancel out, and it would look like that. If ECL is a lot smaller than VGS minus VPH, then it would be a straight line out at some point. So we would expect that this to look like that. It's not a parabola, but it's something like that. So it's a separation between the two. So it kind of makes sense. That's exactly what we wanted to model. So mathematically, it matches the behavior that we have seen before. Now, what's the saturation current? Does the saturation current make sense? It does, right? I mean, it's the saturation current that we have had before. It's W over L, mu effective COX divided by 2 times VGS minus VPH. And then we got this thing that is new. ECL divided by this. I mean, it's the same kind of a thing that we have had before. If you look at the term that divides VGS over VPH, is linear. VGS minus VPH. So we get the term that divides VGS minus VPH squared is a linear term, pushing the equation to look more linear as what we've expected. So linear increase in VGSs causes, for small VGSs, larger jumps in IDS, and then when the device gets really velocity saturated, these jumps become more linear. So this is a model that is actually pretty good for modeling all kinds of things in digital systems. Modeling standard cell sizing, deriving standard cell sizing and deriving delays equations. Okay. Yes.
Could you please go over again what the N is represented?
It's just a fitting factor. So what they did, they picked. So the question is, what does N mean here? This is how the velocity of carriers in all devices, whether they're planar FETs, FinFETs, nanowires, nanosheets, fork sheets, or whatever you like, it always looks like this. Then you have a little more of a curvature, maybe a little more of flat. They found out that the equation of this type models this well. And what else would you use? I mean, you can use something that is log, but log is too flat. So we pick this one as a decent model. Depending on what kind of a device you have, whether it's an NMOS or a PMOS, by picking an exponent, it works well. What you'll find out is hardcore modeling people pick numbers that are in between 1 and 2. That's kind of, I dare you try to integrate that.
And the purpose of taking infinity or like once how high?
Picking and that was my example of a hand model that we used before. That is no good because it doesn't handle stacks correctly. I'll see that in just a second. We can try to look into that. Now, these models have been done by well-known people, and they published these relatively highly cited papers before, which we'll find in, for example, later deployment DC models. And so, when you plot those equations or plot the VD-SAT against on the output currents of a MOS transistor, you get what you expect. Nicely matches. So this is my hand fit versus the simulation. It fits right there. I can try to numerically evaluate that in 28 nanometers, and this is what they get. Let's say that I picked a flavor of a transistor that has VPH of about 0.4. I can calculate what is VD-SAT. And I end up with these numbers over here that are, notably different than VGS minus VPH. I mean, if you subtract VPH of 0.4 from over here, kind of matches down low, but then gets closer to something like this. Bends upwards. In some cases, it does make sense to go to N, going to infinity model, but not always. I mean, if it bends really sharply, that would make sense. So let's take a look at what is the application of these models. The first one is this. How do we size a bit? And we have been talking about N to P sizing or P to N sizing, which is the beta ratio. What did we say for the beta ratio? It used to be 2 long time ago, then it was like 1.6 around 28 nanometers or 45 nanometers. And then when we got down to FinFETs where P transistors became very similar to N transistors, it became more like 1-to-1. But how do you size the stack? What's the magic of sizing the stack? So remember what we said. We want to start with something that's an inverter. It's not that. And let's say it's a FinFET inverter, size 1-to-1. And I would like to make this NAND have the same equivalent resistance as an inverter. How would I do that? this is B. So to make a stack of these two transistors at the same resistance as a stack of one, so let's say that this one has a unit resistance of R, what should be the resistances of these two transistors in the stack? R over 2, right? So how should I size the two transistors in the stack to have a resistance of R over 2? Double their widths, right? Well, that's used to be true. And let's see what is the problem with that. So if I make each one of these two they'll definitely have lower resistance. But at the same time, take a look at this. I put two transistors on top of each other. The electric field that governs the amount of charge that is in there and governs the currents that are inside of there is less. Each transistor sees less of a charge and less of a field. And each one of them is less velocity saturated than it used to be, than a single transistor is. What would that result to the current? If it is by stacking transistors, we make them be less velocity saturated. Will their current, by putting two of them in a stack, be cut in half, or will be cut by less than a half or more than a half? By stacking them, I've reduced the amount of velocity saturation because I've like virtually extended their kind of channel length. Not really, because we're talking about fluids, but we kind of have extended their channel length. So if I put a whole bunch of them, theoretically, I will not be velocity saturated anymore. That's not true, but you just follow this train of thought. So they're less velocity saturated. So will their current be cut in half, cut in less than a half, or cut in more than a half? Somebody should say that, so I don't have to. Come on, quiet people. You need to take prelims and things like that. This would not help your cause, being, I'll take the fifth for the prelim. Come on, more than half. Who believes it's going to be cut in half? Stacking two transistors will cut their current in half. Nobody believes that. Who believes that the current will be cut in more? The current of a stack of two transistors will be less than one half. Few of you believe that? A half? How many of you believe that a stack of two transistors, each of the two transistors in a stack, is going to have more than a half of a current? Nobody. Uh-oh. And the other ones do not have an opinion. So if the device is less velocity saturated, it should have more current, right? We should try to quantify that. So that simply means that if I double the width of these devices, if they're velocity saturated, this equivalent resistance is going to be less than R. So they're going to be, each one of them is going to have more of a current, and their equivalent resistance is going to be less than R over 2. This is kind of hard to think of these things where you're changing not the numerators but the denominators in the equations. That's basic idea here. In unified models, we assume that the VD-SAT is constant. Here, VD-SAT changes depending on the channel length. There is this modifying factor EC times L. I have a mental model that double the length, then my ECL has doubled. And if you go to this equation, I have twice ECL for a stack of two devices. Therefore, my current is going to be divided different. There's a question in the back. Yeah. Okay. All right. So how much does it actually, you take this equation and punch in the numbers that I put before. So, if my starting ECL was 0.75, by doubling the length, it's like 1.5. Again, this is not exactly what happens in the device, but model is going to tell us that. So stack transistors are less saturated. So if I take VGS minus VT, I'm taking this at 1 volt, IV sat is 2/3 of the invert. If you go on, spice this, you'll get 64%, pretty close. So therefore, in order to make a NAND 2 match the current of an inverter, this is how it should be sized. Oops, not that. So if this is some deeply scaled device, this should be 1.1, 1.5, 1.5. If you don't believe me, open up any standard cell library that we have. You'll find this exact sizing factors. How about the stack of 3? To have the same, the current, if you evaluate that, for a stack of 3, does not go down to 1/3, but to 1/2 because of a lesser velocity saturation. And as a result, you should upsize them by a factor of 2. Take a look at any standard cell library and you'll see. Now there is a catch. Here is another mind twister. Let's take a look at 28 nanometer technology and take a look at the, how should a NOR be sized. And this may bend your mind at the moment if you were already confused by this. You'll be confused even more. But take a look at this. So in 28 nanometer process, P and N mobilities did not quite match. They were somewhere in between. So optimal sizing was like 1.6 to 1. How should this thing be sized? Well, a NOR has single NMOS transistors in the pull down, so they should be made the same, right? What should be the upsizing factor for PMOS transistors? Is it the same as it was for NMOS transistors? More or less? So
I just be wrong, but you have like on the one hand, you have the velocity saturation effect working against us, but if you go to shorter channel, you also dim voltage power up. So isn't that like kind of, I don't know if it cancels out, but it's going in opposite.
that's the question here is the Dibble may be canceling out things that are happening here. That is true, but as a secondary effect. Here is what is the thinking. So NMOS transistors here, upsizing factor should be 1.5. if they're velocity saturated, it should be 2 if they're not velocity saturated. PMOS transistors are less velocity saturated than NMOS transistors. They enter velocity saturation later because they have less of a mobility. So their upsizing factor should be closer to non-velocity saturated device than the velocity saturated device. So this upsizing factor here is going to end up, if you look at the standard cell library, is going to be something like 1.8 times that original 1.6 that we had. Or 1.7 times 1.6, depending on what kind of flavor or library you have. This can be mind-bending. You know, this is what is velocity saturated, what is more or less velocity saturated. But that is the reasoning why we see certain sizing in standard cell libraries. It's something that is important to know. It is also important for those, some of you have inclination to design digital circuits, transistor level digital circuits for various reasons, because standard cells don't work quite right. Keep this in mind. You can really get the wrong sizing and suboptimal performance by missing that. Yes.
So the just to clarify, the idea is because that you have the lower saturation curve in the stack state, and you don't need such a high resistance.
Correct, but the answer is also the device becomes less velocity saturated because it has less of a field when you stack it across it. Here is another thing. I rattle these things out, you know, that I want to have sizing that looks like this. .5, 1.5 here, 1 in FinFETs. How do I make 1.5 width in FinFETs? I don't. So the only way to make this work is these would be 2 and these would be 3. Oh, sorry, I did it wrong. These would be 3s and these would be 2s. Okay, so it has to be always an integer, and we're going to have these ratios 2 to 3. These things this gets very intense and very interesting with these next generation FinFETs that we are seeing, or fork sheets and stuff like that, and you need to somehow layer together all interesting nanotubes. People will have a lot of fun, or may just go for suboptimal solutions in some cases. Models are your friends, and you should embrace them for hand analysis, but also for your spreadsheet analysis. Another one. So let's take a look at how does this impact our logical efforts. By definition, in any technology, logical effort of an inverter is 1. So in all technology that is older than 90 nanometers, this would be before we use the strain. So sizing would have been 2 to 1. In 28 would have been about 1.6 to 1, and in FinFET is 1 to 1. As I size an AND in an older technology, this would have been 2 to 1 1. What would have been the logical effort of an AND 2? .5 exactly. When sizing this kind of a device, this would have been 1.6, 1.6. This would be 1.5 and 1.5. So this is 3.1 divided by what did I do here? By 2.6. So that's like 1.2. And in this case, this is 1, 1, 1.5, 1.5. So this is 2.5 divided by 2, which is 1.25. What does this mean? Less. So it's similar, 1.2 is similar to 1.25, but it is definitely less than the 1.5. What does lower logical network of stack gates like NAND2s mean? Mean to you? Yeah, somewhat. I mean, essentially, NANDs or stack devices are becoming better drivers or became better drivers. That was very favorable, right? I mean, we could build more logic in the same number of stages. Some people predicted the end of scaling. There is a paper that was well cited in the 80s from a really well-known faculty at that time at a university across the bay that says the scaling is going to end because of the velocity saturation. People are going to be demotivated to, because the performance is suddenly just not going to be good. Nobody's going to do, use these scale devices. But this was one of the things that actually really helped, is that our logic suddenly closer to inverters and became better. Yes.
It's the second to the back of what I
Right. What did I do here? Oh, I made a mistake here. So this is not right. It's supposed to be 2. 2, 2. So this is 4/3. It's 1.33, right? So nevertheless, my story holds. It became a better driver. How does this work for NORs? This is supposed to be then 4, 4, 1, 1. So this is now 5/3, which is 1.66. So NORs are bad. In this case, it would be 1, 1, and this would be 1.6 times 1.4. Who can do that quickly? 1.6 times 1, 1.6 times 1.8. It's like 3. Let's say 3. So this is about 4/3 approximately, and over here this would become 1.5, 1.5, 1, 1. This is 2.5/2. Implication here is that NORs are now first-class citizens, have become equal to maths. There used to be a bigger penalty for putting a NOR in our critical paths. You'll see different of a mix. So this is just trying, getting some of the rationale. I went slow because I was getting a lot of stares and a lot of these incorrect answers. Hopefully you understood this, that less velocity saturated device means more current, but compared to the reference that was more velocity saturated. So I left off, I have a little small module about the Sakurai-Newton model or alpha power model, which I'll cover after SCCC. All right, thank you.